Okay, one more look at our spring mass system. Suppose I have a spring anchored to the ceiling. I have a mass anchored to the bottom of the spring. When I let that hang naturally, this is its equilibrium position drawn across the page. I then take that spring and I lift it up in the air, squishing the spring. We've already seen in a lab previously in the year that the vertical gravitational potential energy can be ignored, and so as we go to the highest point, we store energy PE elastic as a function of its amplitude at its highest point. After releasing the spring pushes the mass down, reaching a maximum speed at the equilibrium position of negative V, where we have kinetic energy. As the kinetic energy decays and it reaches its lowest possible point at negative A, we end up with potential energy. This repeats over time to kinetic energy and then back to the beginning. Once the kinetic energy carries it back up vertically, it has potential energy, and this whole pattern repeats. It's important to note that even though we have a positive A and a negative V and a positive V, at the ends, the total energy, E, can be described as the elastic potential energy. Whether or not it's positive or negative would be 1/2 kA squared. And then at the middle, or the equilibrium position, we see that the energy is entirely kinetic energy, which is 1/2 mv squared. And this V would also be the maximum velocity of the system. Anywhere else, the velocity would be less. As it travels back up to the equilibrium position, the velocity would be slowing down, reaching zero, and the same going in the bottom direction. So only at this center line does the maximum velocity is the maximum velocity reached. So based on conservation of energy, E equals E prime, we can determine that the maximum velocity is simply calculated by setting those two extrema equal to one another. So if we say that the potential energy at the maximum point is equal to the kinetic energy at the maximum point, then we have a calculation of 1/2 kA squared equal to 1/2 mv max squared. And we've already seen that this allows us to calculate V max as A times the square root of K over M. This was utilized in a previous video much earlier in the year for describing the physical characteristics of a system that was not related. But before we get to that and why that was useful and where that comes from, I also want to mention that at any other point, we know that the total energy, E, would be equal to the maximum energy, E max. Now, for reasons that will be obvious, I'm going to say that the E max value is going to be based on the initial position at PEE. And so what we would say is that any point other than the maximum point, we would have kinetic energy and potential energy that would then be equal to potential energy at the maximum. Now the maximum, of course, is going to be where x equals A, and these points are going to be at any point where x does not equal A. So that would be somewhere here in this middle region from the maximum extreme at the top and the maximum extreme at the bottom. So we can imagine that if we looked at a point somewhere here, the box is moving up, the mass is moving up, but it also has the spring stretched out, and so there is both kinetic and potential energy. And so this would not be V max and it would not be X max. And so what we have is 1/2 mv squared plus 1/2 kx squared equal to 1/2 kA squared, right, at the maximum value. Of course, the half terms are common and can be cleaned up, but if we do some algebraic rearranging here, we can end up with the velocity being equal to v squared equal to, let's see, k over m times a squared times the quantity 1 minus x squared over a squared, which at first looks pretty complicated. However, if we note that V max is a times the square root of k over m, then it's very easy to notice that that term is actually right here. And so the velocity squared is equal to the V max squared times this quantity 1 minus x squared over a squared. And so this allows us to describe the speed of a simple harmonic oscillator as a function that is plus or minus the maximum speed times the square root of this quantity, 1 minus x squared over a squared. And so you can see that the velocity at any point is a function of where it is in relation to the maximum value. Now that's describing this simple harmonic oscillator of a mass and a spring. But what's valuable, and as I mentioned previously, is that it's possible to relate simple harmonic systems. And so if we repeat this idea with a spinning system, let's say that I have a mass m out here on the end of a string, anchored in the center, spun with some consistent original velocity, right? That initial velocity is uniform, and this thing spins round and round and round and round. And so we would say that the tangential velocity is the maximum velocity. And we've already discussed that, the max, as being 2 pi r over t. And of course, if we're looking at a radial system like this, then r is a. And I want to talk about how we got to that point. And basically, the way to relate these two things is if you think about the simple harmonic oscillator here, it's oscillating up and down, and that's a one-dimensional oscillation. The reason why circles are quite slightly more complicated is because they're actually oscillating in two directions, right? If we look at this mass and think about it as being, as it goes in the circle, as simply caring about separating the two directions of motion, right? This mass is going left to right repetitively while it is also going up and down. Now the thing is that because those things are circles, those things are inversely related to each other. As it goes more right, it goes less up or less down, right? And depending on which direction you're going. So you can imagine that as this moves from the radial position here to this position that I have it drawn, as it moves to the left, which it is doing, right? It is moving to the left, it is also moving up. And so if we take just one dimension, which is why I've labeled x here, right? Then this would be A. This would be the maximum amplitude, which would correspond to the radius at that position. Caring only about movement in one direction, we can say that as it moves from this position to that position, it has moved to the left, and its new position is now right where this meets the axis. And so this is x from here to there, right? Now, it's also important to notice that the velocity, since it is now no longer vertically upward, is actually growing to the left, right? As this thing spins, the velocity that was tangentially upward here is now becoming more and more going to the left. And so we can actually depict that as a component vector here, where this is the velocity that would then combine with the vertical velocity in order to create the original maximum speed at a 90-degree angle. The reason why this is useful is that these two triangles are similar to one another. This angle here, theta, is the same as this angle here, theta. And so what that allows us to say is that the sine of theta is both equal to the opposite velocity over the hypotenuse V max, but also equal to the opposite here, which is simply the square root of a squared minus x squared, using Pythagorean theorem, divided by the hypotenuse, which is the radius, which, remember, is the amplitude of the system, divided by a. And so what we can do is we can rearrange this to see that the V max is equal to, or excuse me, the V velocity is equal to the V max times the square root of 1 minus x squared over a squared. And what we just did there is proved what we already knew, right? The velocity of the system is based on the original velocity times this square root term. Now, this formula came from a spring bouncing up and down on a mass, and this formula came from analyzing one-dimensional motion of a spinning object. The point, of course, is that the two things are the same because any simple harmonic oscillator is driven by the same characteristics that repeats over a similar pattern for an indefinite period of time. This is valuable, as we've already seen, in the sense that since these things can be proven to be governed by the same rules, then if we describe the velocity maximum as we have above, 2 pi a over t, then we can solve this for t as being a function 2 pi a over v max. But as we saw in a previous video earlier in the year, the maximum velocity has a proportion to a over v max, as being the square root of m over k. This is where we got our formula for the period of a harmonic oscillator as being 2 pi times the square root of m over k. The point, of course, is that this describes the characteristic period for a harmonic oscillator of a spring that does have a spring constant, but it came from a formula based on circular motion that does not. But that still holds as a valid proof because of the same relationship that we've derived here. The velocity as a function of V max and the square root of this term is analogous, or is not just analogous, but is exactly the same as the formula that we derived here, because any simple harmonic oscillator, these formulas apply. This becomes very useful in the sense that waves, any waves, sound, light, water waves, all are driven by a physical characteristic and mass that can be used to determine period, but also have a speed characteristic of the individual oscillating particles, whether or not it's a mass oscillating up and down or a mass spinning in a circle, that can be driven by this formula. So any proof that we can make with one system can be tacked onto any other simple harmonic oscillator.